Today we turn our attention from the ground up. In our last presentation, we explored the foundation system of the Mercedes-Benz Stadium and examined how it anchors the massive superstructure above. That discussion set the stage for understanding what comes next. This time, we move above ground to one of the stadium's most visually striking and structurally sophisticated systems, the facade. It is a carefully engineered component of the building structure network. The Mercedes-Benz Stadium's facade system was initially explored using a digress design, which offered geometric flexibility and material efficiency. However, as the project progressed, the design team shifted to a diagonal truss system. This transition was driven by structural practicality, ease of construction, and the need to resist large lateral forces such as wind loads. Unlike the die-grid, the diagonal truss system allowed for clearer load paths and simpler fabrication. In the end, while the die-grid inspired early design studies, it was the diagonal truss that shaped the final build structure. Structurally, the facade was not a decorative shell, but an active part of the load path, designed to provide lateral stiffness and help distribute environmental forces such as wind pressure across the building envelope. Each panel was prefabricated off-site and installed on-site as a modular unit. Once lifted into position, the panels were connected to adjacent units through carefully engineered vertical and horizontal joints. Vertical joints accommodated thermal expansion and controlled tolerance buildup over heights, while horizontal joints provided lateral stability and ensured airtightness and weather resistance across panel seams. The precision of these joints were critical in maintaining overall facade integrity and long-term durability. Given the height and irregular curvature of the facade, many crawl cranes were used to position components accurately with tight tolerances. This approach reduced the risk of contact damage and allowed for safe navigation around structural obstacles. Structurally, the panels and cable net were not self-supporting during installation. To provide necessary support from the outset, a series of fin columns, slender vertical steel members, were installed first behind the facade line. These fin columns were strategically aligned with the nose and of the steel framework and served as intermediary support between the primary structural system and the cladding units. They carried particle loads from the panels and cable net system during construction and ensured positional stability until the full structural tension and frame continuity were achieved. The facade was directly connected to the mega column system at key anchorage points, forming a continuous load path from the ground to the roof to the ground. At the intermediate level, fin columns, slender vertical steel members positioned behind the facade, served as secondary structural links between the cladding system and the primary steel framework. These elements played a crucial role in distributing lateral forces collected from the surface panels and cable net into the structural skeleton before reaching the mega columns. Under wind pressure, lateral loads were transferred from the ETFE and metal panel surfaces through the tension cable net, steel frame, and fin columns into the mega columns, which then transmitted them safely into the foundation. This integration allowed the facade to function as an external diagram, stabilizing the outer envelope and reducing deformation along the perimeter during dynamic loading events. In summary, while the facade at Mercedes-Benz Stadium was not a primarily load-bearing system, it played an essential structural role. Through its integration with fin columns and mega columns, it acted as a stabilizing diagram that distributed lateral loads and reinforced the stadium's perimeter during dynamic events. Now that we've examined how the facade performed structurally, let's turn to the materials that made this lightweight yet resilient system possible. The Mercedes-Benz Stadium incorporates approximately 165,000 square feet of single-layer ETFE film on the facade. These ETFE systems are supported by a custom-engineered steel framework tailored to the membrane's geometric and structural requirements. Specifically, the single-layer ETFE panels on the facade are fixed using a system of T-profile clamp supports which are anchored to the primary steel frame at 30-inch intervals. These clamps are designed to grip the edges of the ETFE film while allowing for minor movements to the thermal expansion or wind pressure. Additionally, cable clamps are installed every 5 feet along secondary bracing members to provide lateral support and maintain membrane tension. This support system ensures the stability of ETFE panels under dynamic loads without adding significant weight to the structure. ETFE is an ultra-light weight fluoropolymer, approximately 1% of the weight of traditional glass, which dynamically reduces dead load. Despite its lightness, it offers excellent resistance to environmental factors, high tensile strength, and exceptional light transmission, making it ideal for large-scale transparent enclosures. Through this lightweight and flexible clamp system, the ETFE facade achieves not only functional enclosure but also expressive form, allowing the architecture to breathe, transmit daylight, and perform structurally with minimal material usage. Importantly, ETFE's elastic behaviors allows it to deform under load and return to its original shape, making it well suited for tension applications like cushion systems and curb panels. These properties enable the designers to create complex geometries without relying on massive substructures, resulting in a visually light yet structurally responsive envelope. The supporting steel frame played a dual role. Structurally, it formed the primary support grid for both ETFE panels and metal cladding, transferring loads to the mega column system and resisting lateral forces. Architecturally, its segment geometry was aligned with the stadium's facade, wing-like form, translating aerodynamic inspiration into a buildable skeletal system. The integration of the steel frame with cable net assemblies ensured dimensional precision and surface tension stability throughout the facade. However, despite its distinct design and advanced materials, the facade system was not constructed in isolation. In fact, it was built simultaneously with the stadium's mega trusses, a decision that was not merely about efficiency but one that was structurally and logistically essential. There were three key reasons behind the simultaneous construction approach. First, both the facade and the mega trusses were structurally connected through the shared use of the 19 mega columns. These vertical supports unified the foundation, facade, and roof into one integrated system, making it structurally unfeasible to install one independently of the other. Second, the angular geometry of the facade and non-orthogonal layout of the mega trusses were tightly interlocked. Their connection points required extremely high precision, and sequencing one system without another would have risked geometric misalignments and weakened structural performance. Third, crane operations imposed practical limitations. Both systems required ultra-heavy lifting equipment, and the overlapping work zones meant the dismantling and repositioning cranes separating would have caused major inefficiencies in time, cost, and site safety. By building both systems in parallel, the construction team were able to optimize equipment usage, reduce structural risk, and maintain overall project continuity. In our next presentation, we will explore the mega truss system in greater detail. focus on its long span performance and the engineering challenges it overcame. We will also examine the precise junction integration between the facet metal trusses and metal columns, a critical junction that defines the stadium's overall stability and architectural coherence.